and trying to present what I feel are the opportunities and the challenges in this integration. First of all, let me start by saying that whatever good you see in the slides, that is the merit of credits of my partners in several projects, as Malte said, in particular, the one that you see here, SIG-G NTN. If you find something wrong or something you do not agree with, well, the blame is on me. Most of the results on which I build this presentation come from the SIG-G NTN project, which is an European SNS-funded project with several partners. Beside the University of Bologna was Thales Alenia Space France, acting as technical manager, Ericsson, SCS, DLR, Martel, Thales, Qualcomm, Orange, CTTC, Digital for Planet, and Greener Wave, and Telit for the first 2 years. Then they actually exit the project. Having said that, so the disclaimer is done. Let's go to the outline of my presentation. First of all, as I said, I'm the first speaker today, so bear with me. I will actually spend 4 or 5 minutes on the bridging satellite communication to NTN to introduce a little bit of background. Nowadays, NTN is very well to everyone, but I think that a little bit of common ground will help during the presentation of my fellow colleagues after myself. Then I will go to where we stand today, so 5G and 5G advanced, and then I will actually introduce the role of NTN in SIG-G, which from my perspective is synergy and not competition. And in particular, this is based on smart SIG-G architecture that leverage standard and smart design for a sustainable NTN. I will actually spend 1 slide on the radio access technology research area, so addressing NTN from day 0. So trying to fill the performance gap or to exploit the performance margin that we still have in NTN, and we can actually achieve if we start addressing radio access technology challenges from day 0. And then last question that I always ask myself: what did I say? Which are the messages that I pass to my audience? So without any further ado, the first part is on SATCOM to non-terrestrial networks, so nothing happens overnight. We are not actually witnessed an hype on NTN. NTN is just the result of decades of effort in satellite communication, of research, development, and implementation that actually create what we today call a non-terrestrial network. So I want actually to acknowledge this path. And so let me start from saying that the term NTN that we today use quite widely originates in the context of the 3GPP 5G standardization, which essentially was 2016. From 2016 on, we use this NTN to address what we call the non-terrestrial network, so the use of space and airborne platform, organizing a connected infrastructure integrated with terrestrial network to provide wireless service on Earth. But the key point here is on the space-borne platform, not really on the airborne platform. Let me be pretty blunt here. Even in the very initial studies of NTN, airborne were actually treated as a geostationary satellite with a very nice link budget and with a very small delay, but nothing else than that, just a stationary platform. The key challenges comes from the space-borne platform, and in particular from the LEO and VLEO and MEO constellation. So space-borne essentially means satellite communication. So the use of the artificial satellites to provide communication links between various points on Earth. And if we look at that one, this is where the knowledge that we built in decades of research actually came in help when we defined non-terrestrial networks. So bear with me. This is just one very simple slide, but I would like to point a couple of important aspects when we deal with the satellite communication. First of all, we know that a satellite is nothing else than a piece of hardware that actually circles around the Earth according to Keplerian laws. This is physics, nothing more than physics. It's 17th century physics. So orbits are ellipses with Earth in one of the two foci. If we look at the circular orbits that we are actually seeing today in the market initiative, the Earth is the center of the foci. And the Keplerian laws tells us that when we decrease the altitude because we want to decrease the delay and we want to improve the link budget, then the speed of the satellite increases. And by increasing the speed of the satellite, the orbital period reduces, and the satellite is actually staying on the same small piece of Earth for a smaller time, and its field of view also reduces. This aspect have an effect on NTN. So essentially, the number of satellites that we need for continuous and global coverage increases in low orbits, because essentially we need more satellite per orbit to provide continuous coverage of a single point on Earth. The speed increases, the satellite fly faster around the Earth, so we need more satellite to cover a single point, and we need more than one orbit plane, multiple orbit plane, to provide the global coverage, and this essentially provides what we call constellation. Now, we can actually go brute force and decide to go for tenth of thousand of satellite to provide this coverage, but we can go also, as we will see, through smart design and see that we can achieve this global coverage also with a few thousand, even less than 2,000 satellite. The next point about the orbit of the satellite and the effect of the orbit of the satellite is that by going so fast, we introduce Doppler, but we also introduce delay, variable delay, and differential delay that needs to be managed. And we introduce also multiple and frequent endover for the terminal on ground, because the satellite actually stays on the same point for 5-6 minutes. And if you reduce the elevation angle under which you see the satellite, you can see the satellite for a couple of minutes. So the radio interface adaptation introduced in 3GPP were actually targeted to compensate the Doppler and delay, to adjust the timing for the hybrid RQ, and to deal with endover and spectrum management. So this is essentially the framework, the physics in which we have to deal when we consider the NTN part. So going further, as I said, we introduced modification of the 3GPP in the 3GPP standard in order to accommodate this aspect of NTN. So where do we stand right now? 5G and 5G advanced. When we started, legacy SATCOM systems were typically based on industry-driven technology solution that mainly led to proprietary architecture and protocol stack, which means that a posteriori was really difficult to have interaction with terrestrial system. Everyone might remember bulky phone for specific satellite solution. That was a problem of integration. The solution was very good, and extremely advanced technologically speaking, but was not fully integrated in the market, well, actually separated from the market. Even today, the major satellite operator provides essentially a proprietary solution. You have to buy a specific antenna, a specific terminal, a router at home, and then you have Wi-Fi, not a fully integrated solution. So before 5G, it was actually interworking, mainly interworking between terrestrial and non-terrestrial network. With 5G, we achieved integration. In 5G advanced, as I said, modification have been introduced, and from release 17 on, the mobile phone or whatever, the mobile phone that have chipset compatible with release 17, compliant with release 17, can actually connect to a satellite transmitting an NTN compliant signal. So that's from 5G and 5G Advanced. In 6G, what we are looking at is a full integration and native NTN, so 3D multi-layer network and a native air interface for NTN. In order to get to this point, to the 5G, 5G-A, and 6G specification, a massive joint effort has been placed both from the terrestrial and non-terrestrial stakeholder in developing a global standard and a global air interface. When I say massive, it's really massive. This picture that my colleague Alessandro Guidotti provided this morning, to me, it's very, very interesting. You see the cumulated number of technical documents, TDocs in 3GPP, that have been produced relative to NTN in the past 20 years. You see very well that the number of TDocs increased quite suddenly, almost exponentially in the last years, reaching an incredible 40,000 TDoc presented in 3GPP related to NTN. That's an impressive contribution that has been placed in the last year in order to achieve this TN and NTN integration. In terms of the evolution from those first years of study item to the normative phase, at the very beginning was just a study, was actually trying to bring into 3GPP the know-how of decades of study of SATCOM. So NTN use cases, requirements, key issues and solution already known, brought to the 3GPP, channel modeling and impairment. That was only study. Then in the following years, release 17, 18, and 19 have actually addressed the normative phase. So specification that include NTN as part of 5G and 5G-A. So we started with transparent payload and Doppler and differential delay management in release 17 on S and L band. Then in release 18 and 19, mesh connectivity, regenerative payload, so the G-Node B on board of the satellite, mobile VSAT, and KA and KU band. So there was an extension also on the frequency band addressed by the specification. Then the release 20 and 21 started the study of 6G, and in particular last June, the study item on 6G radio as a specific, included a specific point on an harmonized 6G radio design for terrestrial and non-terrestrial network, including, as I said, their integration. So this is where we are right now, trying to integrate from the very beginning terrestrial and non-terrestrial network in 6G. Just a quick overview, more from the viewpoint of the evolution also of the spectrum. It's very important, this one. You see release 17, just a couple of bands around the 2 gigahertz. Then in release 18, the addition of one band in, again, around the 2 gigahertz, and then FR2 started be present in the specification, and then in release 19, the number of bands allocated to NTN in terms of specification, so standardization, not regulatory aspect, have been increased as well. In this context, which is the role of NTN? As I said, synergy and not competition is my motto, the way in which I would like to present the role of NTN in 6G. And in order to justify this, I use the result of someone else, not my own result. Last March, during the Mobile World Congress, the JSMA presented the intelligence report, which was quite interesting for the NTN. At that time, 60% of the user of cellular systems were ready to pay up to 5% increase to have end-to-end connectivity of their smartphone. And this is a huge number. 60% is a huge number, but that was March 2025. I believe, and I'm pretty sure that if we go out today, we know we can actually ensure that probably that percentage went up to 80 or 90% of the user. Everyone is willing to have a mobile phone able to connect to a network, even if the terrestrial network is not available or is not made available by some situation, natural or political situation out there. The second result of that GSMA intelligence report was that the global market, NTN global market, will account up to 3% of total telco revenues, in particular addressing two main markets. One was the ubiquitous coverage and service continuity, the direct-to-device, and the other one was enterprise and governmental market. The week after the Mobile World Congress, till March 2025, there was another big event in Seoul, Korea, organized by 3GPP, and that was actually targeting the identification of the topics to be addressed in 6G. Out of the 230 contributions presented, 1,800 attendees, NTN was present in 75% of them. AI was present in 78% of them. So NTN was the second topic addressed by those 200 contributions as of importance for 6G. So the role of NTN in 6G is pretty clear. NTN will be a structural element of future communication, of future 6G communication. And this is actually pretty sure. And how can we actually address this part? So, as I said, two main services. One is direct-to-device, direct connectivity to smartphone, service continuity and geographical coverage, including PPDR, public protection, disaster relief, operating below 7 gigahertz. I'm not, Malte? You raise your hand? Oh, okay.
No, sorry.
Okay. And the other one is broadband additional service connectivity to vehicle-mounted device. So vertical markets addressing service operating above 10 gigahertz. One is broadband, the other is more wideband and 4G-like service, the D2D. And we can achieve this through multi-orbit, clearly, and also multi-band architecture. It's not just one single band, it's multi-orbit with two type of nodes. One is deterministic, the one that flies around the Earth that we call satellite in geostationary platform or non-geostationary platform. And the other one are flexible nodes that you deploy opportunistically, for example, in case of emergency apps or heavy drones, or in case of hotspot that you want to cover with traffic and with the system and with the hotspot. Sorry. So how do we move from this multi-orbit, multi-band architecture? What we can provide? So this is actually when I start saying we want to leverage standard and go for a smart design for a sustainable NTN, where sustainability is not just one dimension, it's multiple dimensions. It's not only financial sustainability, it's not only economical, but it's also environmental and societal sustainability. So during the project, we developed a concept of a new constellation, and that concept was mainly to demonstrate also that mega constellation has actually limits. In the first, the limits are technical. There are many problem with the mega constellation. Let's take one, for example, the antenna resolution. Even if you have a lot of space, because you can actually put different orbits at different altitude, the number of satellites that sooner or later will come into the field of view of one terminal requires a very high resolution for the antenna, which is really challenging, which actually put a lot of problem in the air interface and coexistence aspect. There are economical challenges in launching, in managing the infrastructure, in the space crowding, and there are also environmental challenges in terms of environmental footprint, the B production, and the classical well-known Kessler effect that actually tends and threat to make one orbit unavailable for decades if accident occurs when the orbit is too much crowded. So what can we do to do things better with respect to the mega constellation, with respect to tens and tens and tens of thousands of satellites just launched with brute force and not really as very smart communication design? We can do two typical example that we have here that we provided in the 6G NTN project. One is a conventional architecture with all nodes with the same functionalities. And the other one is a distributed architecture with heterogeneous node at the same altitude, but of different dimension, different weight, different power. Essentially, two types of node, feeder nodes with our higher computational capability for most of the RAN core network functionalities, and service node with lower computational capabilities for minimum RAN functionality, and without any connection to the ground segment, connection only to the user terminal. In such type of architecture, you can easily trade off size, power, and weight of the different satellite in order to get to a sustainable architecture, sustainable constellation. In this perspective, this is just an example. You can find more example and more analysis on the website of the 6G NTN project with the latest deliverable uploaded a few days ago. So if you go for a 3GPP compliant radio interface, compliant design, and you do an accurate constellation design and sizing, and you target the T2T case, for example, so no competition with the fiber optic as you go continuous and ubiquitous coverage, you can get at a very nice constellation with an altitude of 600 kilometers with a near polar inclination of 87 degrees, which means that you have a total coverage of the Earth, more than one satellite always visible to ensure handover, 10 seconds overlap between satellite, and 45 degrees of minimum user elevation angle in order to allow TN and NTN coexistence also at spectrum level, then you can achieve a very, very nice number. You see here the comparison of the two architecture, the conventional and the distributed one. The distributed one is the one with the feeder and the service. So you see that the total number of satellites that you have here in this column is well below 2,000 satellites in order to provide a full coverage of the Earth. And in particular, the second one has a total mass lower than the first one, and the total power used for the constellation well below the first one. So what essentially the message that I want to pass is that there's really no need for mega constellation. There's no need for billions of investment. 2,000 satellites can be achieved with a much more lower budget, and it's possible to have sustainable NTN constellation. So that's not 20,000, not 30,000 satellites, is less than 2,000. So this is the message that I would like to pass in the framework of what is the role of 6G, of NTN in 6G. One more step, and then I'm going to the closure. Addressing NTN from day zero is very important in terms of air interface. In 5G and 5G Advanced, we built on top of something that was already defined for terrestrial networks. So we actually introduced those modifications, allowing NTN to perform well without too much impact on the terrestrial network air interface. In 6G, we can do better than that. We can start from the very beginning and thus not just get very good performance, but get excellent performance by integrating from day zero. And from our perspective, what we need to do is to look into the multi-carrier waveform enhancement in order to relax the synchronization requirements and go towards what we call GNSS-free operation. Reduce the PRPR for spectral efficiency maximization. So that is for the multiplexing and multiple access aspect of the waveform. In terms of modulation and coding, we need to go towards lower SNR regime. The PPDR and the ubiquitous communication requires also to communicate with very challenging radio link conditions as those that you can encounter in light indoor when you want maybe to talk to someone, even if you are constrained in your house. GNSS-free operation improve resilience and reliability of the system by removing external dependency. It's sadly known to everyone that by jamming the GNSS, the GPS, you can actually block communication via satellite right now. We need to go GNSS-free. AI-based physical layer to improve performance. I'm not advocating here to go for a full AI-based physical layer, but some of the feature of the physical layer, some of the function can be substituted in particular by ML algorithm and improve performance, such as channel prediction or channel estimation. Flexible uplink and downlink framing structure, TDD support, dynamic TN and NTN spectrum sharing, all related to the maximum efficiency of the spectrum. And distributed beamforming, as you have seen, we have 2 satellite minimum invisibility, but in some area of the globe, you have multiple satellite invisibility. So techniques that tend to exploit multi-transmission point are really available and are really helpful. And then joint communication and positioning and joint communication and sensing. And this is very important. The first one, because actually it tends to help the GNSS free communication by providing position, navigation, and timing through the infrastructure. The second one provides low to medium resolution sensing capabilities directly integrated into the waveform. These two together actually tends to modify the ultimate goal of the infrastructure. So instead of bringing one bit from one point on the Earth to the other point of the Earth, so instead of working as a very intelligent dumb pipe, the infrastructure can provide information, generate information itself. Information related to the navigation, information related to the sensing, thus becoming an information provider and thus being a sustainable infrastructure also from the business model perspective. Ending my talk. So what are the key takeaway messages from for me, at least for me? Synergy and not competition is the first point. So NTN is an integrated technology. NTN needs to go towards a business technical framework where MNOs, SNOs, and hybrid network operator can successfully cooperate. It's not a winning solution that of going for NTN as a substitute of the terrestrial network. This is not where we want and where we shall go. We need to leverage a standard and smart design to achieve a sustainable NTN. And in particular, we need to use the 3GPP features in particular. So unlike direct to cell, NTN as a feature that allows the integration with TN. We need to go for research aspect related to the progress of R&I, demonstration and standardization. In particular, we need to go into standardization of the interface from day zero but we need also to avoid the revolutionary approach. We can't waste whatever has been done through the year, just starting from scratch again in 6G. And finally, beyond the integration of communication and sensing, we need to integrate also navigation in order to transform the NTN from a mere dumb pipe to a source of data, which will make the infrastructure sustainable also from a financial point of view. So NTN represents indeed the new, probably the last frontier of wireless communication. It's an infrastructure which will be able to allow people to connect irrespective of their geographical position, political situation, and natural condition. Is really a true anywhere and anytime communication system that we are building with 6G. And with that, I end my talk. Thank you very much.
Yeah, thanks a lot, Alessandro, for this very insightful talk about the network architectures in the 6G system integrating NTN and TN and the challenges that need to be addressed in this context. I think it was very broad and insightful. We have several questions. I think we're a little limited in time, so let me pick up only one, and then I would ask you to address the others in the chat window. So the calculation you've shown on the satellites that are needed for full coverage globally, that has impressed several people. And there's a particular question, and that says, under what conditions and requirements 2,000 or less satellites would be enough? Can we generalize this takeaway? Yeah, Alessandro, what can you comment on that?
For the details assumption, you can. So first of all, thanks a lot. For the detailed assumption, you can actually refer to the 6G NTN deliverables on architecture. We reported all the data. And yes, we can surely generalize for that one. Clearly, if, as was reported in my slide, that assumption were to provide, let me call wideband communication. I'm not saying fiber-like communication. I tend to oppose to the fiber-like communication, fiber-like services for LEO configuration. We have actually solution for that as well. So the calculation was mainly for direct-to-device communication in order to provide communication, as I said, in area where you need that, not necessarily within a town super crowded where satellite has nothing to say. I hope that can help. But again, details, assumption are on the deliverables of the project.
Okay, yeah, thanks a lot, Alessandro. As said, there are several more questions, but I fear we don't have time to address them online now, so please take care for them in the chat afterwards now. With that, let me quickly change. Okay, no, okay, with that, I would like to announce our next speaker. That is Symeon Chatzinotas. He will talk about sustainable NTNs. Symeon is a full professor at the University of Luxembourg. He's also an adjunct professor at the Norwegian University of Science and Technology. He received numerous awards and recognitions, including the IEEE Fellowship and also an IEEE Distinguished Contribution Award. He has also been actively involved in numerous research projects on national and international level. And the most recent one to mention is the 6G ESA project, where his research group also had the coordinator role. Yeah, probably for those of you who don't know, ETHER was also a large NTN project, and it was funded in the same call as the 6G NTN project. So there's some direct relation. With that, I would like to give you the floor, Symeon.
Excellent. Thank you very much for the introduction and for the organization. I'm very happy to see so many people connected. So I will spend the next 25 minutes trying to give a sustainability spin to some of the research that we have been doing here at the group. Before I go into the details, just some words about who we are. So the group has been operating for 15 years now, almost 16. We're about 100 researchers working closely with many well-known industrial partners. So satellite communication is something that we have been doing for more than 50 years since we started, before the evolution to non-terrestrial networks. And lately we have a particular flavor of looking into massive antenna arrays, quantum communications, and so on. So moving on, I'll try to address this topic, and I will try slowly to narrow down the scope so we can talk about some of the things that communications engineers can help with. So ideally, you know that NTN is very broad, as Alessandro mentioned before. So I think the main question is, if you would like to make it more sustainable, which of these layers would you have to improve? And of course, it goes without saying that for different reasons, satellite is the most active, and as a result, the most, I would say, power consuming of all these layers, because the number of mega constellations that we are seeing being announced and flown increases on a daily basis. So essentially focusing on satellites specifically and letting on the side for the time being hubs and UAVs. Let's see what has been the evolution. So satellites they come in many flavors, but it goes without saying that lately the vast majority of the activity is on the LEO satellites, and that has changed a bit the perspective, because in the past you had one very large satellite and you need like one launch to put it out there and it would stay up there for 15 years. And now we see that we have to replenish our satellites every 5 years, which is good for the technology, but not very good for the sustainability. And obviously there is a lot of launching and relaunching effort that obviously has to take place. It's true that we have some reusability in our launchers, but it doesn't solve the problem that we need many more launches now to put a LEO constellation up there. Now, on the other hand, you have the terminal side, and in some cases, this is, let's say, to our benefit in terms of sustainability. So you see that in many cases, we have these large parabolic dishes that now they are being kind of miniaturized in these flat panels, which they are very widely used, and they're still kind of consuming materials and power. But the next step, as we discussed before, is how to have direct connectivity to the handheld. And that's somehow to our advantage in terms of sustainability, because there is one handheld that supports many, many networks, and it means that we don't need to have separate devices, separate terminals, for example, for terrestrial and non-terrestrial connectivity. Again, in some specific cases, but that's something that we can be happy about. Now, moving on, sustainability comes in many shapes and flavors. So essentially, I will try to stay out of topics that are not really in my area of expertise. So for example, what happens with debris? What happens with sustainability in terms of astronomy and how well you can observe the sky? That's different scopes of sustainability. I'll try to focus on the essence of resources. And again, resources, what do we need? We need fuels, we need materials, and that has to do very much with launch and manufacturing, not so much with the actual communication process. Then you need spectrum, sustainability spectrum, which is also heavily regulated, and this is not where we can make a difference from one day to the next. And then you have the orbits and the power that you consume, and these are really the assets that we can really talk about. Now, the main, I would say, the main hype or trend is that if you want communication performance, you need to have a larger payload, or you need to have denser constellations, which automatically will lead to higher launch costs. So the two main players today, they address this from a different perspective. So Starlink tries to have many smaller satellites, whereas AST is trying to have a sparser constellation, but really large satellites that kind of unfurl and deploy into 20 by 20 large antenna arrays. So we have to keep into mind that we cannot solve all the problems. And if you see at the bottom of the table, this is how we moved from single LEO satellite to LEO mega constellations. So the space segment is still important. So this is where we're going to be focusing. The launch is dominant, and of course there is progress being done there, but this is not something that the communication engineers can fix necessarily. And the ground segment is also increasing. But at this particular talk, I will try to focus on the sustainability of mainly the space segment and how we can make it more power efficient, right? And before you just saw the top right, this star clouds video, which, you know, I let it as food for thought and critical thinking of whether you think this is sustainable or not. Essentially flying data centers with 4 by 4 kilometer solar panels in the sky. I'm not. I haven't reached a verdict yet, but it's a good discussion for the comments later on. Okay, so what can we do about it? First of all, how can we bring in AI to help? So AI can do many things. It can accelerate, so we can get timely, near optimal solutions if you spend a lot of effort training in advance. And this can be useful, very useful for the ground segment, but not so much for what we're trying to do here, which is essentially reducing the power that we consume on the space segment. So on the satellites, where a generation now comes somehow by default, we need to have near optimal solutions with a few joules. And that is actually possible in specific cases. And I will explain when we can achieve that. By the way, I have all our relevant references in the slides that will be shared later on in case you want to look into more details on that. So, first of all, the exercise that we try to do is we write a survey and we try to flesh out the important use cases, like, for example, how you can reduce the complexity of the FEC, which is one of the most power-consuming aspects of a transceiver. Payload reconfiguration, so when you have to do resource allocation, and even Earth observation application where you can reduce the amount of data that you would like to communicate. Going back a bit into the concepts of semantic communications and so on. So of course, not all platforms are suitable for this. And if you look in our reference, we have tried to put all the relevant platforms together and we have classified them in terms of capacity, memory consumption. And at the end, we try to have a conclusion about what would make sense in terms of flying it on a satellite, what AI chipset can actually fly. And I'm talking about AI chipset that can be both off the shelf. So in that sense, the idea is that you don't do everything on space. The training is very expensive. So you have to pre-train your model on the ground where you have a lot of computational capabilities and power. And then you upload your weights into an AI chipset and you do inference on the sky so that you can save some of the energy which is being consumed up there. And obviously, less energy, it means smaller satellite, it means less cost in terms of launching it. Now, we have been looking at different platforms in that respect, starting from FPGA or GPU-based, but at the end, the ones that seem to be more promising for lowering the consumption of the power is the neuromorphic-based approaches. And I will explain why. So this is how a spiking neural network more or less works. So the idea is that you spread your input and output in binary time sequences. So you can see it as a quantization problem. So instead of feeding real values, you feed the network a sequence of bits, and then you get a sequence of bits as output. And in principle, this can save you a lot of energy. Of course, this doesn't come for free. Obviously, if you have a fixed clock, it means that it will take you more time to get some inference out of this spiking neural network. This is something that we have actually proved experimentally based on actual AI chipsets like Loihi 2 coming from Intel. And here you can see one example. This is for a payload reconfiguration exercise where we can get better in terms of a couple of orders of magnitude in terms of saving energy, and this on the right side. And on the left side, we see what we have to sacrifice, which is the execution time. And the comparison is always to some classic CNN or convolutional networks. So again, the outcome or the takeaway message here is that for certain cases that you don't want to be very fast, then you can really save on how much energy you need up there, and you can make your entire payload more sustainable. Now, the second topic I want to touch is this kind of integration of multifunctional payloads. And this is not difficult to understand why this is sustainable. So far, we have been really looking at all the space functions as completely separated. You have your own payload, you have your own spectrum, and you separate your systems and orbits completely. But what if we could do this design in advance? We can do it jointly, and we can save on satellites and number of flying elements. So that touches both the sensing, where you can have some interesting joint cases like object tracking and verification. So you can do it both with, let's say, SAR-based methods and communication-based methods, or even security countermeasures for interference and jamming, which means that you're receiving some jamming from a specific angle of arrival, and then you use SAR to identify exactly where this is coming from. Same goes for the LEO PNT, in the sense, since we fly all these LEO satellites, what if we had some small payload, integrated payload, that could help us replace the GNSS or even complement the GNSS satellites that we currently depend on. So we started working on this 2-3 years back. We have a couple of projects now, and I will explain how we approach the problem. So essentially, we're trying to bring communication, sensing, and PNT in the same platform. We want to decrease the mass and the volume of this integrated payload by reducing as much as possible the consumption. And we have a step approach to go in that direction. So the first step is working on these cooperative payloads. So the idea there is that you don't share everything. You start by sharing only the RF front end. So you have maybe a very capable antenna array, and you want to share this resource among all your functions. So in that sense, you could have a radar payload that wants to scan or swap an area. You can have a PNT algorithm that wants to get as much coverage as possible. That would be the blue coverage area. And you might have a communication system that wants to create a multi-beam structure. And all this can be generated nowadays by a common front end with a capable antenna array. Moving forward, we would like to unify both the frequency and the hardware. So right now, everything works on very separate frequency blocks. But we know that the activity goes up and down over time. That's true for communications specifically. So we would like to be able to use this common spectrum using CDMA, TDMA aspects, even the space SDMA aspects, and being able to dynamically over time reorganize how many resources we use for each function. And then, of course, we need some temporal mitigation, some space-time adaptive processing to handle all the residual interference that you have from these multiple access schemes. And of course, the Holy Grail, which is very active area now in the literature. Not sure if it's the best solution, but it's, I would say, the most challenging solution, is to have a joint waveform. So you have a joint waveform that can do sensing, positioning, and radar. And then, of course, you have to achieve a certain amount of trade-offs so that all the requirements of these three separate functions can be achieved with the same waveform. So we started already with some papers that you can already find in the literature, but our objective now is a project with ESA that was recently acquired, and we're going to build some prototypes, software, and hopefully lab also prototypes, mainly focusing on monostatic and bistatic cases, trying to demonstrate some of these, let's say, fusion of different functions in the sky. And we're going to start to begin with, at least with the communication and sensing. So this is how at least you can make multifunctional payloads work to your benefit in terms of sustainability. Now, last but not least, we're going to talk about intelligent antennas. And antennas is essentially a very important aspect. You can see what we have achieved in the top right. So this is the AST antenna. We have removed the noise amplification. We have achieved a lot of directivity. But of course, there is a lot of room to grow in that dimension. For example, we could go for satellite large antenna arrays, which are other deployable. You have the electromechanics. In orbit assembly, you have to bring in robotics colleagues there. Or then cohesive satellite swarms, which worry more about the synchronization. But the specific part I want to talk about here is the metamaterials and these new antenna concepts that we have been seeing in the communication theory community. So one of the most active areas today is the beyond diagonal RIS, which is essentially a concept of reflecting signals without taking them back to the digital domain. So using a lot of flexible interconnections in the analog domain to reflect the signals. And there are many flavors of that, so I will not go into the details. But the main question is whether we can implement something like that on NTN and make it power efficient. Now, you can find already many papers out there about this, but I'm a bit skeptical when it comes to RIS as signal relays, because the NTN link budget is already very weak. So we need to have very ideal reflection coefficients. Also, we have very large propagation delays, which means that if you want to coordinate different elements in the sky, like base station and RISes, that makes it much more challenging. And very often we have the propagation geometry, which means that we have to cross an element, and the element is somehow in between our link that is coming from the sky and having to go to the ground. And that can really act as an obstruction unless you are willing to put two antennas on your flying element. So this is useful if we can implement it as satellite antennas, and then if we can manage to reduce the swap, right? And then you have seen that there are all these interesting concepts about holographic communications, which they're not so far from RIS. Essentially, you can work with stack intelligent meta surfaces, and then you can achieve this holographic gain, which hopefully we're in early stages, so we have to work more on that, on prototyping, but we would like to see whether we can get, with a low mass and power footprint, a very nice directivity. And the main benchmark there is whether we can do better in terms of the classic antenna arrays that we are working on, right? But there is hope because essentially the holography works as an entire element, and you don't have these kind of independent finite elements that you have to coordinate to achieve directivity gain. Of course, there's always challenges. You have closed loop versus open loop approaches. We need prototypes and practical models, size weight comparisons, as we said, but it's a promising avenue to create more sustainable antenna arrays, which is one of the bulkiest and most power consuming elements of the payload. So with that, I will wrap up. And if I would like to put those ideas from a short-term to long-term aspect, I would say that we are doing very well in terms of metamaterials and prototypes. So I hope we'll be able to see some of these technologies coming into the payload soon. AI chipsets in space, we already have prototypes, a few of them, but I hope that we'll see more of them as the technology progresses, especially looking at the European Space Agency plan. Then distributed satellite systems where we kind of coordinate very large antenna arrays. And last but not least, the multifunctional satellite systems, which require a bit more of a joint effort, but they would pay off much more if we achieve them in terms of sustainability. And with that, I will conclude just some publications and projects that you can find more information. And thank you very much for your attention.
Yeah, thanks a lot, Symeon, for this very enlightening talk which was covering the sustainability aspects of the space segment. So the different options or the different parameters that can be considered there and where the potential lies. That was indeed very insightful. We have a few questions on the chat, so let me turn to them. There's one question on the ISEC for bistatic cases in ISEC. Is the synchronization between satellites a particular challenge within NTNs?
Yes, I would say that this is the main challenge. I think in terms of how we optimize our directivity, our beamforming gains, pre-coding, we have done a lot of progress there. Synchronization is the last remaining bottleneck. And of course, we're talking about bistatic cases, right? In the monostatic, you have to worry more about your self-interference. But in bistatic cases, you have to worry about the synchronization. And then we're looking at two cases. One case is that essentially you want to make sure that you have very tight synchronization between the satellite that's transmitting the signal, the pulses, and the one that is receiving them, because you want to process it on board. Or the other case is that you're actually sending and dumping all the signals. You are kind of quantizing them, sampling them very accurately, and you're sending them back to the cloud for processing. And then, because you have much more advanced processing capabilities, you can afford not to be fully synchronized, because you can solve the problem with advanced processing. But if you want to do it on the sky, you really have to rely on tight synchronization between your two satellites.
Okay, thank you. Then there's another question, which is quite interesting because it focuses on the space usability of FPGAs and AI platforms. So in particular, the question is, do the AI platforms and FPGAs support the space radiation environment? And what is the strategy to achieve both performance and reliability in that context?
Yeah, so you can find both approaches out there. So there are attempts to space harden FPGAs. Of course, this is always a very long, tedious process, and of course, the element will cost much more. Or the other approach is you just rely on redundancy. So instead of flying one off-the-shelf component, you fly more of them. And if one fails, you have quick methods to switch to the other one. So these are the two competing strategies, I would say, to make sure that you can resist radiation. We have studied both of them, but this is just, I would say, simulation architecture based. I cannot say which one would be the best if you actually fly something. So we would have to fly and try it eventually.
Okay, thank you, Symeon. Then I have another question. You mentioned the holographic communication that is enabled by the metamaterials, and if I understood correctly, you highlighted as one of the key benefits that it will significantly reduce the weight of the payloads. So it's a kind of a physical, so it addresses the physical weight. Are there also other advantages of this technology foreseen, in particular if you consider it in the space as antennas for the space segment, for example, energy efficiency or something like that?
Yeah, so in principle, here we can work much more effectively by stacking metamaterial surfaces and making sure that the gain comes progressively as the signal propagates through these surfaces, instead of just relying on a larger aperture. Right? Because the large apertures, we know they are problematic in terms of making either the satellite larger, or you take the risk of opening them in the space environment, where it's always something can go wrong, and then you lose the entire benefit, right? So the idea is to have something compact that gives you the same directivity as an antenna that would be much larger. And now, as a technology, it has other benefits as well in terms of being able to create multiple beams towards multiple users in the same frequency or at different frequencies. In the literature, it has a lot of benefits also for near field. But at the end, I think for the satellite use case, we don't care so much about the near field. Everything's far field to us. So we just have to take the benefits of the SIMs and metasurfaces that are suitable to our use case.
Okay, thank you, Symeon. So probably we have time for one last question. There's one in the chat on the waveform, OTFS. This is a way to reduce complexity in the satellite and hence power requirement. Oh, okay. I think it's more a comment. Yeah, but probably you can say something on that. So
yeah. So I think OTFS is very promising as a technology. It has a lot of advantages, and we have been investigating as a community and looking into that. I'm a bit skeptical if we're going to manage to convince the standardization community to switch to something else, because we have seen that at least the past few releases, not major changes have happened in that respect. So I think it's very relevant if you have the capability to design your own legacy system. But if you have to comply with some standardization requirements, there might be some obstacles to get there.
Okay, thank you. Yeah, that is a good point. So especially when it comes to standardization, we experienced in the last generation where some members tried to introduce a new waveform, that there was a lot of resistance. So you need to have, as you said, you need to have very good arguments if you want to push for a new waveform there. Okay, just another question came in, probably we can have also that one. For the reconfigurable intelligent surface between satellites, RIS can support laser communication of ISLs, so inter-satellite links. What is the key technology for laser communication of RIS satellites?
So essentially, now we see that ISLs are mainly supported by optical, and I would say it's a mature technology now. You have vendors, it's really flying and being used by constellations nowadays. They're not using metasurfaces at the moment, but in the literature, there is some work that is trying to apply the RIS concept for optical frequencies. It's much more challenging, obviously, because we don't have the same type of wave propagation that we have in the RF. I'm still skeptical to see how it can go into the space domain and how we can justify this, because the optical terminals that we have, they're already compact and efficient. So we have to see whether it makes sense to have something which is only based on reflections and not really something that can work as an integrated optical terminal. So I think that's the main comparison that has to be done, and it has to be done in the context of the swap restrictions that we have in space. I haven't seen any study like that, but it would be interesting to do such comparison and see who comes on top.
Okay, yeah, thanks a lot, Symeon. I think we have all the questions, but probably to be safe, you can also check the chat if everything has been answered. If not, you can also take care for the remaining ones offline.
Thank you very much.
Okay, perfect. Thank you. Yeah, let's come to our third speaker now. That is Tomaso de Cola. He will talk about the next frontier of edge cloud continuum. So Tomaso is the head of the Integrated Satellite System Group at German Aerospace Center, in short DLR, in Germany. He has been involved in different standardization activities in ETSI, IETF, and other organizations. Currently, he serves as an area director of the Space Internetworking Services. He has also been involved in many research projects funded by the European and the Italian Space Agency, as well as the European Commission, and he held several roles there, among those also project leader and coordinator. And his main research activities are in the field of TCP protocols, satellite networks, delay-tolerant networks, and protocol architectures for space systems. So with that, I would like to give you the floor, Tomaso.
Hey, thank you, Malte, very much for the kind introduction. I hope you can hear me well and you can see already the cover of my presentation. So, as just introduced, the topic I'm going to present is kind of a continuation of the nice journey that was started today with Alessandro and with Symeon before, and in a way is also a bit provocative in that we see a little bit how far, realistically speaking, we can go with computing in space, or integration of computation between ground and space. That pretty much is something that is attracting attention of many people at research and industry level, and that historically has been addressed from the terrestrial community for what regards edge cloud continuum, so the computation that has to happen in a continuous way across the different kind of layers of a terrestrial infrastructure. Before doing that, however, I wanted to give a short introduction about DLR, the German Aerospace Centers, that is the Federal Research Institute of Germany, that is composed of, let's say, two main faces of the same coin. On the one hand, we are a research and technology center addressing a number of technologies and not exclusively dealing with aeronautics and space. We also address energy, transport, security, and defense, and then there is the National Space Agency. More peculiarly, for what regards my institute, that is the Institute of Communication and Navigation, we address the very different angles that are nowadays reality with the satellite systems, from the networking part, physical layer, RF and optics, but also other aspects that are more in the direction of other, let's say, verticals or applications that are making use of the satellite systems, like aeronautics and nautical systems, and so on. And we have in particular 4 main missions from a strategic standpoint, in which the main one for my department, the Department of Satellite Networks, is the global connectivity for people and machine. The vision we have is indeed related to the unification of the so-called 6G, 5G before, with the inclusion of the NTN component from day one. And in order to achieve such a vision, we have been working, acquiring a number of projects in the last few years, either coming from a European Commission, from ESA, or also funded by our national ministry that are somehow reported here. In particular, I would like to focus today with my presentation about the work that is being done in 5G Stardust. That is the project I'm coordinating, that is closing, however, March this year, so in a couple of months. Nexasphere, that is a project that I'm the technical coordinator, and Unity 6G, where they are also member of a large consortium, that are all dealing with different aspects of edge computing. Then, obviously, the overall foundation from a system architecture standpoint comes from the 6G NTN project that Alessandro mentioned at the beginning of his presentation. And then there are a number of other activities that were carried out or are still happening, like Agrarian, that are towards the use of edge computing in space under different flavors. But let's go direct to the point, take into account what is, let's say, the vision that we have. That means unification. And unification essentially means NTN as a native component of 6G from day one. There are different building blocks that can be considered for reaching such an objective. Today I'm focusing on the one in the center of this given year, that is the Edge and Cloud Continuum. Edge Cloud Continuum is quite a fundamental player here, because this is the role that has been played in the last couple of years, in the last decade, in the general terrestrial infrastructure, towards a more service-oriented architecture. That is also the one depicted here. In this case, obviously, including the case of NTN, so a satellite constellation integrated with the rest of the ecosystem. Why talking about edge cloud, edge computing for satellite? Maybe we can go back a few years when there was the initial time of edge computing for terrestrial networks. There was a very inspiring paper, on the Follow Me Cloud concept that was essentially about the fact that user, while moving, may want still to get access to their data, personal data, in case to get some computation done according to their own cloud. And obviously, in the case of mobility, that is not so straightforward. That's why we need to have a kind of cloud moving with you, so really a concept of Follow Me Cloud. We may think of something like this, having in mind the case where the user may be fixed, but the data centers, the cloud facilities, the edge computing functionalities are instead moving, and are moving because are on board the satellites. And there's this kind of shift of paradigm, or seeing, let's say, the same picture but from a different perspective, can be considered an interesting motivation for understanding, or even questioning whether such a picture is really possible or real for the accomplishment of edge computing in space. But realistically speaking, what does it mean? So what does it mean is thinking of the so-called multi-access edge computing functionality, MEC, deployed in a 3D integrated CGN NTN infrastructure, where we have a number of assets that are also in space, like GEO, MEO, LEO, drones, apps, and so on. And we also have the counterpart on ground, either in the terrestrial infrastructure or directly on the end user. So we have a kind of distributed and sparse implementation of edge computing, and obviously the question here is how to make sure that the user demands in terms of task, computation, and so on can properly reach the servers located in space, or generally speaking, it's possible to select what is the best server in terms of availability, capacity, and so on amongst those available in ground and space, and maybe even reaching a kind of collaborative approach among the different assets available from a communication standpoint. There are, a matter of fact, different flavors of edge computing in space that may come up immediately. We may think about Earth observation, surveillance, and so on, so that the computation and the generation of data happens directly in space, so that the edge computing starts natively in space. Or there will be the case where data are generated first on ground, like IoTs, but it's not only IoT. And as such, some data processing must be performed, and the possibility will be to do this in space. Obviously, this depends a little bit on the scenario, use case, and the verticals. There are scenarios where still terrestrial infrastructure is the preferred one. There are other scenarios where a combination of space and ground is also appealing, and there are other scenarios, especially in the case of rural area, rural infrastructure deployments, where the availability of satellite is favorable against the poor or completely missing terrestrial infrastructure. Why making use of edge computing in space? Well, we know that historically edge computing has been always intended as a kind of boosting performance in terms of reducing latency, and as such can be really used to overall reduce the service latency that can be experienced, but also in the case of satellite, making better advantage of the intrinsic geographical coverage that is offered by satellite constellation, geosatellites, and so on. So that in this respect, the use of edge computing in space assumes a particular importance in order to serve a number of use cases that otherwise should still be experiencing a non-negligible delay. This is somehow confirmed by some past forecasts about the market exploitation with edge cloud computing functionality in space, or their application in the general satellite setup, with expected revenues in the order of several billions of dollars. This is something that recently I checked is slightly lower than this. I found yesterday values around $10 billion, but then obviously this depends a little bit on the specific sector that we are addressing for the use of edge computing, but without really switching to the numbers. The point is that there is a market that is growing, and there are big expectations for this. If we think on a practical use case, obviously one possible one is the case of smart farming that is being developed in a project the LR is involved. That is the agrarian one that is funded by European Commission under the Horizon Europe program, where we have different applications in the domain of smart farming, like livestock monitoring, vineyards, and so on, where a large amount of data is being produced, being generated, that necessitates some rapid processing in order for the policymaker and the decision making to take the necessary decision, and then either implement automatically the decision on the respective field of application, or decisions that are first shared with the farmers and then in turn are eventually implemented. But let's go deep to better understand what can edge computing be for space systems. Obviously, we have to start with the basics. That is, what is edge computing in the general context of terrestrial infrastructure? And the general picture is the case where we have a client application like on a UE, then we have the remote server where the other side of the application is sitting. And we may want always to get results, to get information in a more rapid way. That means not always going to the remote level, but having something closer to us, that is the edge level. In order to achieve this, we have this framework that is the one being standardized by the ETH multi-access computing effort, where we have this Mac app that really instantiates a dedicated service by means of a dedicated Mac host that allows to accommodate a number of functions that as such fulfill the request, the demand from that specific client app. While we think to transition this to Edge Cloud Continuum, obviously we have in mind a more complex picture where in the picture we don't have only the edge part, but we also have fog and cloud, so a more dense and sparse distribution of assets aimed at providing computing functionalities. And once again, if we think of smart farming and NTN in this general framework of edge cloud and cloud computing, we have kind of a pyramidal setup with different layers where the user may get access to the different computing functionalities, and these functionalities are pretty much related to different aspects of those data processes, like data filtering, fusion, processing themselves, the distributed computation, and the fact that the results are eventually shared to the final users or back to policy decision maker in order for them to acting remotely and perform the necessary operation. In this respect, NTN can play as a glue element in order to interconnect all the main functionality elements together and then achieve better performance or the necessary performance, especially in the case this smart farming is happening in remote areas. In order to achieve this, from an architectural standpoint, we have to think how to position the different elements that I've just presented before. That means the main actors, the verticals, so the UEs, the transport layer with the satellite, the aerial and the terrestrial part, and the different functions that are pertaining to the Mac layer. So processing, storage distributed across this logical layer. And then there is the other side of the network where there are possibly the final consumer of the data, or as I said before, there could be the overall decision-making chain. If we go a little bit further than that, having in mind the standardization process happening in 3GPP, also in there is a strong focus, obviously, in edge computing that is somehow synergically happening with the work done in the aforementioned ETH MEC, so that the two can provide the full picture of the edge computing architecture, taking into account, on the one hand, more the 3GPP architectural vision, and the other side, more the interfaces definition. And this becomes even more interesting when we think of the use of these concepts for NTN. That's why we have here the case of a constellation with the space in space edge computing, and we have the different elements that may intercommunicate one with another by means of dedicated interfaces like Edge 1, Edge 4, 6, and so on. And we need obviously to place a GNLB and a UPF function in space in order to make use of the available online edge data network that is directly implemented on board the space. So it's quite a complex concept that, however, is the one necessary at first glance in order to achieve this edge computing, the overall picture of a 3GPP native NTN system. If we think in more detail on how to achieve this, we have the GNLB, UPF, the Mac platform, all co-located on board the satellite. We may think also more of a distributed architecture, also depending on the specific disaggregated runs for the functional split option that is being considered. But in general, this is what we can think as reference for achieving this edge computing in space. Obviously, from an architectural standpoint, looks everything easy and straightforward, but as a matter of fact, there are also important aspects to be taken into account, and that comes from the fact that in case of satellite constellations, that is the more natural candidate for deploying edge computing in space. We have a limited visibility of few minutes, possible frequent handover, and as such migration of data or tasks from one satellite to another. And as such, there are also a number of networking aspects that has to be taken into account, because while we think of deploying a Mac in space, we think it's just a matter of deploying a server in space. We also have to make sure that the overall network of servers in space is not congested, so that we are able to achieve some kind of load-aware offloading process across the different servers in space. At the same time, we have to make sure to have some sort of flow and congestion control. And then there is the routing, so that across neighbor, or in any case, the different nodes composing the edge computing in space, we are able to reroute data or requests from one node to another. In the case of a specific node that was initially targeted as the one responsible for data communication and data computing, is eventually not able to do that because the server is either not available, not working properly, or in any case is saturated. That's why we need also an important or a consolidated framework for allocated users to the corresponding server in space, and more important, to think of which server should be allocated to that user or set of users from a protocol and dynamic standpoint. And this is something that typically goes under the name of Mac host discovery, and that plays an important role to make sure that the overall edge computing concept can be really finalized. Sometimes is also worth considering the fact, as also exploited in the Mac FSG specification, to allow for some Mac to Mac communication that could be very useful in the case we want to go for some data distribution or edge computing collaboration across neighbor instances of the same Mac framework, or just because, as in the case of satellite, some data context computing functionality migration is needed from one satellite to another. For a specific user, this can be achieved by means of virtualization, that we don't really going to physically move a function from one place to another, but we just perform some kind of intelligent duplication in order to make sure that the user is still in contact with his own data, or in any case, if the demanded computational task can really take place in the way it was expecting. And what I wanted to shortly talk about is indeed the problem of creating a mapping between the service and the server, because this is not an easy point, mostly because of the fact that the satellite constellation is moving. In the case of a terrestrial infrastructure, from a topological standpoint, is a bit easier, this kind of problem, because typically the infrastructure is somehow rigid, and it's possible to counteract any possible problems or need of exchange of routes and so on, according to the existing protocols and strategies. When we move everything in space, or even more interesting, when we have something in space and something on ground, we need of something more advanced, something take into account the different degrees of freedom that such a feature put in evidence. There are key aspects, several servers, but also different services, because it can be that satellites may offer different services to different users. In space, we know computation and storage is not happening the same way in terms of numbers than what offered on ground. The association I said before, and the fact that the task forwarding might be needed in case a given service is not available, and then we have to route data or demands on the next hops, and this can happen on the routing function available in space, or from a Mac perspective, what I mentioned before, the migration of data from Mac to the neighbor Macs. The performance optimization can be obtained by different means, obviously. I'm just reporting some results coming from a recent paper presented last summer. the main framework was about optimizing service delay and energy efficiency. Of course, a number of KPIs may come to mind, and also several allocation strategies are possible, from the most basic one, like a random allocation of users to servers, or taking the nearest satellite and then increasing a little bit the complexity and also making the solution more refined until reaching the point of deploying some AI-based approach in the form of hierarchical reinforcement learning that really helps in achieving better performance in such a distributed network. There are obviously at the horizon new trends and challenges, because every day we hear more and more about the need of having super powerful satellites for more advanced applications, or just because we need to put more and more 5G functionality in space that, of course, is not for free. There are, on the other hand, as we observed before, limitation for what regards to the capability in terms of power, storage, and computation, so that thinking of just moving some edge computing functionality or also a full data center in space is not so straightforward. Also thinking of what are the components typically used on ground and those used in space, as depicted in this picture, where there is an important gap. Nevertheless, recently, probably many of us have heard and read all these announcements about putting in space a powerful GPU, going to the direction of a data center in space, full AI in space. Also, this I'm linking to the nice slides that were presented before by Symeon. So there are different aspects that are kind of opening the door to more advanced, maybe even more exotic implementation of what we know pretty well on ground that could happen also in space. But obviously there are also some aspects that still need additional investigation and understanding that relates pretty much to the fact that we have to think, first of all, whether putting this dense and massive edge computing functionality, cloud computing functionality in the form of a data center is really the holy grail, or in case the future of this comps. So is this really profitable? Is this what we really mean and expect also from a business exploitation standpoint? Then the other tricky point that is largely debated nowadays in many mailing lists, websites, some publication, and so on, is that one of the possible motivation for moving or to having at least a data center, big data center also in space, is that somehow the problem of cooling that we are experiencing on the ground data centers can be really solved this way. But the corresponding question is then how this may work in space, how heat dissipation may really happen with such a large platform in space, because we know more or less how it works with the satellite, where this problem obviously is there, so that there are the necessary building blocks towards the thermal control, the dissipation through emission, and so on. But then if we have a very large setup, is this still working? And in this, there are interesting discussion, and there are kind of two very different kind of set of people. So one claiming that this is not possible at all, other that instead are thinking on new ideas, new strategy to making it possible. And then last but not the least, as usual, there is the trade-off between what can be interesting to be done, maybe from just an experimental standpoint, but also what is the business benefit coming out of it. And such, just to conclude, certainly we see the value coming from multi-access edge computing, maybe in the form of edge cloud continuum, and this especially as part of a larger picture with the 3D 6G NTN overall framework as part of the general 6G ecosystem. There are a number of points that are still necessitating investigation. Some of them will result in a specific engineering path, And then there is also the point to understand to which extent we can really go for a large edge computing or cloud computing mega system in space, or if on the other hand we have to think of this in-network computation functionalities as to be kind of be isolated in space with respect to specific services, and as such we could stay with the current concept of a spacecraft and satellite. This is obviously an objective and in general a subject that is taking more and more interest, and we have to see in the years to come whether there will be the necessary and sufficient research support to solve all this issue, or if on the contrary we'll have still to wait for the progress and the evolution of technologies from electronics and so on to make sure that more advanced concept of edge computing in space can be achieved. So with this, I'm closing the presentation. So thank you very much, and obviously I'm very happy to answer any questions you might have.
Yeah, thanks a lot, Tomaso, for this very interesting talk, which elaborated on the question what edge computing can mean for a space system. We have one question here in the chat that is addressing the current state of the art. It says, is there some integration already of MAC service in other types of NTN nodes available, such as hubs or UAVs? And I would also extend the question by saying, what of these concepts that you presented are already available in space today in the satellites?
Well, let's say that edge computing, in the sense of computing on board, is something that certainly is something being exploited, for instance, in the context of Earth observation satellites, where there is on board advanced data processing, compression, so because obviously with the more advanced sensoring devices for satellites, the Sentinels, and so on, with regards to the Copernicus European systems, the images are increasing in quality, but also in size. That means that we cannot anymore just dump raw data, but we have to perform some processing on board in order to make sure that we do not saturate the overall capacity of the feeder link, or in any case, we don't need a too long time to dump the data. And on the other hand, there is also the fact that, as also motivated by some 4 or 5 years ago, some papers that there could be the potential of doing some advanced feature extraction, pattern extraction in space by collaborative means across neighbor satellites belonging to the same constellation. But this is more for the future. For today, as said, is more data compression and data processing, most in the Earth observation domain. Then, obviously, the future is to see to which extent this can be also translated more in the direction of general data processing, and then embracing also other sectors like data coming from ground. I was mentioning before smart farming, IoT in general, and so on.
Okay, thank you, Tomaso. Then I would have another question, probably a short one. Does these MAC concepts for application MAC in space, does it have any impact on the routing architecture that we are considering in the, especially in the mega constellations that we have up there?
Indeed, the routing has to play a very important role. Of course, we can think of two main configurations. All the satellites of the constellation implement a MAC agent, a MAC server, so that essentially the routing MAC to MAC will be pretty much the same as the nominal routing we know for data forwarding. Of course, there might be some more specialized routing depending on specific metrics, more of interest for the MAC application. Then there is the other side, the other option, where the MAC servers are implemented actually on a subset, like a clusters of the nodes. And in that case, we have to think of another layer of data forwarding, of task forwarding. That is what I was mentioning before, like MAC to MAC cooperation, but still necessitates routing at underlying level. So that routing for sure is an important aspect to be taken into account. And nowadays, with the progress in optical ASLs and so on, we have more and more ingredients to make sure that we have advanced routing for enabling such concepts.
Hello, Tomaso. So let's come to our last speaker. Last but not least, we have Miguel Ángel Vázquez with us, who will talk about the practical challenges of 6G NTN. And I guess it is no coincidence that 6G NTN is also the name of the corresponding project, because CTTC is, as far as I know, also being project partner in that project.
Yes.
So some words on Miguel Ángel. He's the head of the Space and Resilient Communications and System Research Unit at CTTC Research Center in Barcelona. And besides being a telecommunication engineer, he also holds a degree for computer science. And as the others, he and his group has been very much involved in the European research projects in the past years. And his research interests areas are in the intersection of machine learning and optimization techniques for communication systems, with particular emphasis on satellite communications. And with that, I give you the floor, Miguel Ángel.
Thank you, Malte, for the nice introduction. Let me know exactly. So, how much time should I have? Should I close at 5 minutes to 4 or?
Well, I think we can slightly delay by 5 minutes maximum. So I would say you have until 4, and then we can have the last 5 minutes questions.
Then it's better. Okay, yeah. Perfect. Well, thanks again, and thank you for everybody for, I guess you can hear me well, and you see my screen right now, right? It's correct, yeah. Okay, thanks a lot for the invitation, and I'm very happy to be here with such a big audience. Yeah, so basically, I wanted to complement my colleagues, my talk, to talk to 3 topics, okay? Direct to cell, space data centers. I saw also Tomaso mention a little bit, and then Geo versus Leo. Okay, so let's go quickly so that you can have 3 take-home messages, and that's it, okay? Okay, let's go to direct to cell. I complemented versus modified terminals, right? So the concept of direct to cellular was introduced by Starlink, in fact, a few years ago, and the idea is a bit different of what Alessandro presented at the first time, right? So at 3PP level, what has been done so far is that the user terminal needs to be modified and needs to do some changes in order to combat the satellite channel, right? But then there are other group of people that what they do, it's another approach, right? So what they're thinking is let's focus on unmodified smartphone. The motivation for that is very clear, no? You already have the smartphones of the market, right? I put you here the companies Starlink, ASTSP, that also was mentioned by Symeon, but also I also include you Link here, right? They are also focusing on the fact that, okay, let's focus to unmodified terminals. The problem of that is that you need to resort to non-standardized solutions. You need to find out private or GNOT bits for that, okay? And let's take a look to what implies for every case, no? So on the downlink, so if we want to target unmodified terminals, the problem is whenever we want to detect the downlink signal from the space, we will see a huge Doppler, right? Then this means that the frequency range that I should test is very large, right? So then probably all the terminals, if I don't do anything, the terminals will not be able to detect the first downlink signal, right? With the terminals that we all have in our pockets. So in order to help those terminals to detect the signal, so what we can imagine what they are doing, we don't know because it's a proprietary solution, is that they are doing a pre-compensation at the transmission side, right? Then, but in reality, what happens is that Doppler, it's geometric magnitude, right? So you can only compensate the Doppler on a single point on Earth. Then there is a range of Doppler around that point that the users will be able to detect the signal from the space, right? So meaning that currently we are talking about beams of 600 kilometers at the S-band, but then if we focus on that maximum carrier frequency offset that we can deal with, then those beams should go to 90 kilometers, right? And then my operational region that I can only work is 90 kilometers. In addition to that, in the uplink, apart from the CFO that I need to pre-compensate at the G-Node B, there is the problem also of compensating the timing. As you know, in 5G, there is we are working with time on advance. So basically, the user should know when to send the signal so that it arrives to the G-Node B at specific time instant, right? Then, of course, the terminals are not prepared for that huge delay. And then what we can do is to try it again at the G-Node B level, try to compensate that, right? And but again, the delay, I can only compensate on a region over the Earth. And then meaning that at the end of the day, the region that this time compensation can be done reduces the beam size, okay? And this is a problem, right? Because at the end, there are many people that is focusing on the time to market, but this means that the radius of the mean should be reduced for each case. And this has some economical implications as well, right? Because you cannot deal with a large number of users. And of course, you need to be able to have antennas that are able to do this very reduce radius, right? So what in the other philosophy that we see today is the UE is performing all of these compensations, right? So meaning that we cannot rely on as much of we have today, but the UEs should do the time compensation and the frequency compensation, right? And in order to do so, what is being written on the standard right now is that we should know the position of the terminal on Earth, and then we should require some data from the satellite regarding the position of the satellite. And with that information, we should be able to compute the Doppler and the position of the satellite, and then be able to compute the Doppler and the time that we need to compensate for each case. Of course, there are problems because this TLE or this position of the satellite may have errors. Or also the terminal might not be able to decode the SIM. We call it the SIM19 because it's the control message that the terminal should detect, right? And then it becomes a problem, right? And we try to solve that in the project 5G Startup, which is coordinated by Tomaso. And in our implementation of our release 17 UE, what we implemented is, okay, we know that every certain period we are receiving the position of the satellite. Then we need to create let's say, an estimation of the position of the laser, where it will be in few milliseconds, right? Because otherwise, if we rely on the information that just the satellite is providing, the timing errors that we obtain are very large, right? So we are talking about microseconds, and in fact, the minimum requirement that we have, it's about 1 microsecond. So then if we implement this, let's say, constellation propagation at the terminal, so it should run at the terminal, I should be able to know where my satellite is in the future, then I am able to compensate that in about nanoseconds. The other topic that we are working regarding this is the use of FR1 numerology in KJ-band, right? In the project Trantor, what we are doing right now is together with Grupo Poesia that they build this flat panel antenna that you can see here that is being tested on the anechoic chamber. And this week we are being tested with an Ispasat satellite in KJ-band. The idea is that we are able to test if we can manage the phase noise of the geo satellites with an FR1 numerology. Okay, so the good thing of FR1 numerology is that we can start from 5 megahertz scenario, and in 5 megahertz, let's say it's very adequate for small terminals, right? So when the terminals are very power hungry, the uplink, we can reduce a lot the transmit that we need. But of course, the problem of this numerology is that the subcarrier spacing is very short, and this impacts a lot the carrier frequency offset estimation. So right now, what we are doing is to test it with a phased array with a geo in KJ band. Hopefully, in the future, we will also test it in LEO. Okay, so if we go to the AI in space, the data centers, another topic that it looks that there is a lot of interest. I complement what Tomaso was saying. I would say that there are, I don't know, it's becoming a hype already, despite of Thales Alenia Space did a project with ESA 1 year ago, but we already saw a Google moonshot on that. I recommend that paper. It's on archive. They talk about also some economical impact on having AI in space. The concept is very simple: is that we process and store data in space, and the motivation there are the different things: the reduced carbon footprint, and also this cooling design that the heat that you can have on the space is more convenient than the one that you don't have on it. In any case, if you are able to have space-grade processors, manage to do a constellation on that, there is still a problem of connectivity, right? So I did some numbers in another project, and it was related to what we have today on the data centers, right? So within the data center, we are talking about 200 terabits per second between the processors, so 200, 800 terabits per second. And between data centers, we are talking about 18 terabits per second. Of course, if you compare that of today, the data centers, you compare to what we have on the market right now. I know there have been very tests on Earth for free space optics, but right now what we know is on the inter-satellite communication from TESAT and Mynaric, it's about 10 gigabits per second and 2.5 gigabits for inter-satellite links. So we are talking about a huge gap if we want to mimic that data centers of the space, right? So we are comparing hundreds of terabits per second versus gigabits per second. And we are talking about the numbers of today. Of course, in 10 years, everything will grow. So we see that there is a lot of work to be done, right? Regarding the connectivity, if we want to really have data centers of the space. When I was preparing the presentation yesterday, there was a new thing, and I wanted to include you here because there is a new constellation that says that it's going to have 6 terabits per second. And now we are getting closer to this space to ground terabits per second. But again, if we want to have the same to what we have on Earth, but on the space, still we have a connectivity issue, right? Then, in order to solve this problem, there are many. So what we saw at CTTC is that there is we need to increase the space to ground, let's say, free space optics capability, right? So we have been taking a look to a relatively old paper regarding all optical machine learning using diffractive deep neural networks. So the idea here is that they use passive optical elements in order to do convolutional neural networks, right? And there have been a lot of implementations, and there is quite a promising technology for all optical machine learning, right? So the idea is to be able to detect images at the speed of light, okay? And what we have tried to do is to do this for OIM communications, right? So I don't go into the details because I don't have too much time, but the idea is that in OIM, you are able to multiplex optical signals in the OIM domain. Okay, so and we have been simulating how these passive optical frames should be optimized in order to multiplex these signals, right? And we managed to do that. We did some simulations regarding 6 OIMs. And then the idea is that those 6 values that you can see here, there are photodetectors, and you have 6 photodetectors, and those photodetectors can go to a gigahertz per second the detection, right? So you are able to compensate the OIM problems with at the fully optical domain. Then last thing is, I don't know if I have time. Okay, let's go very quickly. There have been a lot of discussion about LEOs all the time, as you can see, but still GEOs are being launched, right? So there should be a motivation for that, right? And the main motivation is that for some specific use cases, and when we take a look to the euro per bit or regional coverage, this makes sense not to deploy a global constellation, right? And it's very clear that there are a new trend of small GEOs, and there are people actually doing new applications with GEOs. So my point is that we don't need to just focus on LEO solutions. So GEOs are still very valuable for some applications. In any case, you should put the capacity where your users are always, and for doing so, you basically rely on beamforming. The problem of doing beamforming on GEOs is that if you want to implement a direct radiating array, and you need to recover this 30 dB path loss that you have between LEO and GEO, or maybe to GEO, you need a lot of antennas, right? So if you want to have a direct radiating array in GEO, you need more than 5,000 antennas, okay, with the elements that can cover your coverage area or your desired field of view, right? So in order to solve this problem, it's not the first time that this has been shown, but there are few groups that are taking a look. It's a solution called phase array reflector. So where you have a phase array and you have a reflector, in this case, it's not intelligent, right? It's just a passive element, right? And then your gain of the system comes from the reflector, but then you still can do beamforming by your phase array. The way of modeling it is you can have this waveform analysis and with your signal and the separation, and there are many trade-offs, right? And one of them is the number of antennas that you can use, right? So if we focus on the case that we have the same bandwidth and the same size of the satellite, and we want to increase or reduce the number of antennas, you can do it, but then you start having grating lobes, right? And then the more antennas you have on your satellite, then the less available bandwidth you will have, okay? And there is another trade-off regarding the focal distance, so how I approach my phased array to the reflector. So every time there is an optimal position regarding the focal plane, that there is only one, let's say, line between your phase array to the reflector, so there are no, and your beam is the shortest one, the one with the lowest halving beam width, but then the gain is very reduced. So if you allow the focal plane, the reflector to construct your signal from your phase array, you will have more gain here. So there is no clear gain. So there are the different options. So we did this for a company, and we take a look to the capacity, right? So this information theory, So what we did is to compute the dirty paper coding capacity, taking a look that every time we have more antennas, your bandwidth is reduced, right? Because we want to keep the complexity of the satellite as it is. And then what you can see here that the maximum is obtained with a reduced number of antennas, and there is an optimal point for the focal plane distance, right, between the distance that I have between the phased array and the reflector. So just let's go to the conclusion. So I show you 3 topics. I would say the first one is that you need to understand that 3GPP has gone to one direction, and maybe right now we have a SpaceX more active in the 3GPP. Maybe we see that there is a trend to keep the smartphones as they are right now or not. So we will see what happens. But there are some problems if we use legacy terminals, right? Data centers of the space, there is a challenge of connectivity, as you can see. There is a huge complication there. And then we need to take a look to how these solutions are incorporated to the satellite. We have seen that with analog optical computing, eventually we can have some benefits. And then, of course, do not forget about geo. And if you want to do beamforming with geo, with active antennas, normally you should rely with this type of reflectors, right? And that ends just to let you know that at CTTC we have Ispasat Lab as well, that we have a close collaboration with the Spanish operator, both at RF and optical. We have infrastructure for non-geostationary satellites, and in our group we have quite a large number of people. We are coordinating different projects from ESA, from EUSPA, from Horizon, and we are in total around 20 people. Right? Just to at that end my talk. I don't know if I went to.
No, you're perfectly in time. You're perfectly in time, Miguel.
Okay.
Thanks a lot. Thanks a lot for a very insightful talk. This time we learned about practical challenges, and when it comes to the satellites and the different constellations, what issues we still face there. And in particular, it was interesting to hear this connectivity issue that you highlighted when we really think of deploying data centers in space. We also have a few questions. Let's come to those. There's a question on, well, I just read it out. In order to estimate the position of a satellite, UE gets a signal from it and uses angle of arrival or SMT or similar. If this is the case, the satellite will get further away while the signal is propagating through the UE. How can that be overcome? Do you use other parameters?
No, basically well, first of all, the first time you connect with the satellite, you don't have any information, right? So you need to do a special UE for trying to detect the signal from the satellite. So the receivers as they work today, they do not work, right? Then if you basically have this information from the control plane called SIP19, that they tell you the TLE, which is the position and the velocity, right? And this information is updated every hundreds of milliseconds, right? So basically, with that information, you should estimate where your satellite will be and apply the changes accordingly, the compensations accordingly.
Okay, thank you. Then there's another question that I think targets in a similar directions, also on the TLE. Does the UE receive an updated TLE through the terrestrial network, or is it provided by the satellites? So what happens
by the satellite, yeah.
Okay, and what happens when the UE is out of coverage?
When you don't see, well, if you don't see a signal from the satellite, then you cannot connect. You cannot synchronize. You need to do the attachment, yeah.
Right, as simple as that.
Yeah.
All right. Good, perfect. Then thanks a lot. Let me quickly check. No, that was the only. These were the only 2 questions. Yeah, we are very well in time now. Yeah, with that, I would close our session. Let me just give a further note. So for further editions of our 16G open lectures, please check regularly our 16G website. You find it at 16g.org. You can also check there for other activities that we are organizing there. And I guess, well, it's likely that there's something of your interest. So stay tuned and check this webpage regularly. So that was the announcement in our own interest. Then I would like to thank all the presenters again for very insightful talks and discussions. And yeah, with that, I would release you now and wish everyone a very nice rest of the day. Talk to you next time. Thank you. Bye.
Thank you. Bye-bye.